Hi, my name is David Schlivko, and I'm a graduate student in the physics department here at Princeton. Before I tell you about my research, I'd like to share a story about a trampoline named Bob. Bob was no ordinary trampoline. He grew up in a loving household, and Bob's family made sure he drank his milk and ate his veggies every day so he could grow big and strong. But one day, darkness came over Bob's neighborhood, and he began to notice some changes to his body. The strangest part was that Bob's rim had stopped growing, while his rubber kept stretching and sinking off the edge. Bob was confused and embarrassed, but being well versed in physics, he knew one thing for sure. This weird phase of his life couldn't last forever. From the rate at which his rubber was stretching, Bob extrapolated the time it would take for a single atom to stretch across his entire rim, an obviously impossible scenario, and used that as an upper limit on how long it would take to get through this. He waited patiently for the darkness to subside and for his growth to return to normal. As you might have guessed by now, the trampoline story isn't real. It's a metaphor. In reality, Bob is short for the observable universe, and his rim is what physicists call the Hubble horizon, marking the farthest distance one can possibly see from our location here on Earth. Recently, well, just a few billion years ago, that Hubble horizon genuinely stopped growing the way it used to, while the space inside it continues to stretch at a rapid pace, making distant galaxies look like they're getting farther and farther apart. It's possible that there's a physical substance permeating the universe that causes this behavior, and if that's the case, then figuring out what it's made of is a top priority for cosmologists. For now, we haven't gotten much further in this quest than giving this substance a mysterious-sounding name, dark energy, and using observational data to roughly predict its pressure and energy density. But I wanted to explore whether we can also shed some light on this problem from a theoretical perspective, using relatively new results emerging from the field of string theory. You see, space isn't made of atoms like Bob's rubber was. But some string theorists predict that there is still a smallest possible length that could ever realistically stretch across the entire Hubble horizon, the Planck length. If this conjecture is true, then dark energy can't stick around and make the observable universe behave strangely like this for more than about 1 trillion years. And the fact that it has an expiration date can help us narrow down hypotheses about what dark energy might actually be. One of my ongoing research projects uses this approach to analyze the plausibility of a particular hypothesis involving new particles called axions. I think we're still a long way away from fully solving the mystery of dark energy, but to me, every step of progress is meaningful when the goal is to understand the nature of the universe itself.